First of all, I would like to thank the organizers for the opportunity of give this talk. This is a joint work with Walter Carvallosa from Florida International University in USA, José Antonio Méndez Bermúdez from Benemérita Universidad Autónoma de Puebla in Mexico, and José María Sigarreta from Universidad Autónoma de Guerrero in Mexico. We are going to talk about analytical and computational study of the variable inverse Sumner index. A topological index is a single number that represents a chemical structure in graph theoretical terms via the molecular graph. And this quantity, this number, correlates with a molecular property. It's used to understand physicochemical properties of chemical compounds. These indices are interesting since they capture some of the properties of a molecule in a single number. Of course, there are hundreds of topological indices since the seminal work of Wiener. Why are these topological indices useful? I would like to recall that we just know about 1,000 benzenoid hydrocarbons. But if we just fix the number of benzene rings, and we think, for instance, in the number of 35 benzene rings, we have over this huge quantity of possible benzenoid hydrocarbons. And so it's very interesting to have a tool in order to modeling their physicochemical properties, in order to study or predict properties of currently unknown species. Topological indices based on n vertex degrees of edges have been used for more than 40 years. The best known of such descriptors is the Randex connectivity index, or simply Randex index, defined in this way, where UV denotes the edge of the graph connecting the vertices U and V, and dA is the degree, the number of neighbors, of the vertex A. There are 1,000 papers and a couple of books with this in studying this index. An important family of degree-based topological indices named Adriatic indices was put forward. 20 of them were selected as significant predictors. The inverse sum index is one of them. Since this is a significant predictor of total surface area of octane isomers. This index is defined by this formula, which is equivalent to this one. In the last years, there is an increasing interest in the mathematical properties and the application of this index. We study here the properties of the variable inverse Sumner index defined for its real number A as this expression. Note that if we take the value A equal to -1, then this is the inverse sum index, which is useful in applications. Also, If we take the value A equal to minus 1.95, we obtain an index which is a significant predictor of standard enthalpy of formation. We recall that the idea behind a variable molecular descriptor is that the variable is determined during the study in order to obtain that the error of estimate for a study property is as small as possible. And so we can obtain a better ability in the prediction. The aim of this work is obtain new inequalities for the variable inverse sum their index and to characterize graph extremal with respect to them. Some of these inequalities generalize and improve previous results for the known inverse sum in the index. Also, we want to remark that many previous results are proved just for connected graphs, but our inequalities hold for both connected and non-connected graphs. Of course, through this work, we denote by G a graph which is non-oriented, finite, without multiple edges or loops. And we also assume that the degrees are different from 0. So we don't have isolated vertices. This graph represents the carbon atom skeleton of an organic molecule. Vertices represent the atoms and edges the bonds. Our first result relates our index with some important parameters of a graph. If delta is the minimum degree, capital delta the maximum degree, and n the number of edges, and a is a real parameter, then we obtain these inequalities, these lower and upper bounds for our index when a is a positive number. If a is a negative number, we have the converse inequalities. And these inequalities are sharp. In fact, the equality in each bound is attained, and we know precisely for which graphs it's attained. In fact, the equality in each bound is attained if and only if G is a regular graph. Recall that a graph is regular if every vertex has the same degree. The following result relates our index with positive and negative values of the parameter. If A is a positive number, we have these bounds, and if A is negative, we have the converse inequalities. And as before, these are sharp inequalities, and the equality in each bound is attained if and only if G is regular. Well, the general sum connectivity index is defined by this formula. This is important since it generalizes many important indices. If alpha is equal to 1, then we obtain the first Zagreb index. If alpha is minus 1 and we multiply the index by 2, we obtain the harmonic index. And if alpha is minus 1/2, we obtain the sum connectivity index. The following result relates the variable inverse sum there and the general sum connectivity indices for any real number except for 0 and 1. We have this inequality for a greater than 1. We have these inequalities if a belongs to the interval 0, 1. And if A is a negative number, we have this inequality. Furthermore, the equality in several of these bounds is attained if and only if each connected component of the graph is regular. Note that if we consider the case A equal to -1, we obtain this known inequality for the IC index. In fact, it is well known that this index is at most 1/4 the first Zagreb index. Hence, this theorem is a generalization of this classical inequality. Well, I would like to explain the main ideas in the proof. We are going to compute the minimum and maximum values of the function f defined in this way. Since if we have these bounds for C1 and C2 for the function f, and we choose x is equal to du and y equal to dv, we obtain immediately these inequalities. Okay, and now if we sum in every edge of the graph, we obtain the inequalities for our indices. Okay, and so we start with the study of this function. In order to do this, we consider this function with the restrictions h equal to 1, and also we consider positive values of x and y. Note that g is equal to f under our condition. Okay, if h is equal to 1. And of course, by homogeneity, inequality for g with these restrictions implies the same inequality for our function f without restrictions. Okay. First of all, if x, y is a critical point for our function g with the restriction h is equal to 1, the method of Lagrange multipliers gives that there exists constant lambda such that we have these equalities. This implies that x is equal to y, and since we have the restriction h equal to 1, we have that the values of x and y are that, and the value of g is this. If a is greater than 1 and x goes to 0, then y goes to 1 and d goes to 1. Okay, and now if a is greater than 1, we have the minimum and maximum value, sorry, the infimum, which is 1 in this case, and the maximum value, which is 2 to the power a minus 1. And the equality is obtained if and only if x is equal to y. Okay, and of course, since we have these inequalities for the function g, then by homogeneity, we have the same inequalities for the function f. Okay, if now a belongs to the interval 0, 1, then now 2 to the power a minus 1 is less than 1, and we have the converse inequalities. And of course, the lower bound is attained if and only if x is equal to y. And so we have the same inequalities for the function f. In a similar way, we can obtain the result if a is a negative number, And recall that if f is bounded by these two constants, then we have these inequalities, and by summing up, we obtain our desired inequalities. And this finishes our proof. Well, thank you very much for your attention.